Welcome to the second part of the essentials of the course Energy Supply for Buildings, in which we will handle the concept of primary energy and CO2 emissions. All the conversion processes described in part 1 convert primary resources into useful energy. The primary energy is a measure of the energy content of the primary resources used. The useful energy is the energy demand that you have learned to calculate in the course Energy Demand in Buildings. The efficiency, ET, of the conversion system is defined as the ratio of the useful energy coming out by the energy input, therefore as the ratio of the energy demand and the primary energy. So, if you have a heating system, let's say a gas boiler, with efficiency 0.7, this means that only 70% of the energy contained in the gas will be actually used to heat your building or your hot tap water, and 30% will just be lost with the exhaust combustion gases, that is the E out lost in the figure. For all systems in which something is burned, and for the systems based on a chemical reaction like the fuel cell, the energy content of the fuel is called the heat of combustion. Sometimes it is also referred to as calorific value, heating value, or even specific energy. The heat of combustion describes the maximum quantity of heat that can be obtained by full combustion of the fuel. Combustion is a chemical reaction of the fuel with oxygen from the air. See here, for instance, the formula for the combustion of methane, producing heat and combustion products like carbon dioxide and water vapor contained in the smoke. It is possible to determine the energy content of each fuel by measuring the heat output resulting from complete combustion in a very controlled setting. If you are searching for these heats of combustion, there are plenty of tables on internet. Note that you will find two different values, the so-called lower heating value and the higher heating value. The lower heating value refers to the heat released by the combustion process up to the moment that the fume temperature has decreased to 150 degrees Celsius. The temperature of the combustion process itself is much higher, around 300 degrees Celsius for wood and up to more than 2000 degrees Celsius for gas or coal. When it comes to the higher heating value, the idea is that the water vapor contained in the fumes can be cooled back to liquid water at a temperature of 25 degrees, which releases additional heat. This additional latent heat of condensation is accounted for in the higher heating value. The efficiencies in this course are all based on the higher heating value. This table shows higher and lower heating values of typical fuels in kilowatt-hour per cubic meter or per kilogram depending on the fuel. This is therefore the primary energy per cubic meter or kilogram. Observe that gaseous and liquid fuels typically have a higher heating value ranging between 9 and 12 kilowatt-hour per cubic meter. For biogas it is lower. An interesting exception to this is hydrogen, with a very high energy content per kilogram compared to other liquid and solid fuels. When it comes to solid fuels, the last rows of the table, including biomass like wood and straw, you can observe that their heating value is generally lower. These heating values will help us to calculate the primary energy use and the CO2 emissions. But what about non-combustible renewables? Although the concept of efficiency is also very useful to size energy conversion systems using non-combustible renewables like solar panels, we will consider the primary energy of these renewable sources to be zero, as there is no resource depletion nor emission. Let's look now at CO2 emissions. Combustion is a chemical reaction of the fuel with oxygen from the air, producing heat and two combustion products, carbon dioxide and water. So, each time we burn a fuel, it produces carbon emissions. You see in this table emissions of some common pure fuels. Pay attention to the fact that the specific CO2 emissions may be expressed per kilogram or cubic meter of fuel, but also per kilowatt-hour energy content based on the higher heating value, which is the same as kilowatt-hour primary energy. In other words, if we take the example of methane, 1 kilogram of methane will produce 2.75 kilograms CO2 during burning, which is the same as saying that methane produces 0.18 kilograms CO2 per kilowatt-hour primary energy. All fuels in the table have a higher CO2 production than methane. Fuels like hydrogen that do not contain carbon molecules have no CO2 emissions during combustion. Note that would have been attributed CO2 emissions. These are the carbon dioxide emitted during combustion, no matter if reforestation is applied or not. We have defined what the CO2 emissions of fuels are, but is it what we are talking about in policy documents where CO2 reduction targets are set? Well, not exactly. We are interested in CO2 emissions as they say something about global warming. Global warming is a measure for the emission of substances that absorb infrared radiation reflected by the Earth's surface, resulting in an increase of temperature in the lower atmosphere. Global warming is not determined solely by CO2 emissions, but also by many other greenhouse gases, like methane itself or nitrous oxides N2O. The global warming potential that you see in the third column of the table is a measure of the comparative effect of different substances on global warming. The reference is the global warming potential of CO2, which is set to 1. Methane has a much higher global warming potential than CO2, 25 times more. Nitrous oxides even more, 298 times. And look at the global warming potential of hydrofluorocarbons used as refrigerants in heat pumps. If you look now at the last column, you see the greenhouse gas emissions in CO2 equivalent per kilogram substance, and you see that they are of course identical to their global warming potential, GWP. So, 1 kilogram of CO2 released in atmosphere is just 1 kilogram CO2 equivalent. 1 kilogram of methane released in the atmosphere has the same effect on the global warming potential as 25 kilograms CO2, and so on. Most national policy documents and emission factors refer to CO2 equivalents and not only to pure CO2 emissions. It is not about CO2, but about global warming and greenhouse gases. Natural gas, although it consists predominantly of methane, also contains ethane, propane or butane in various shares. It may also contain CO2. All these gases can cause global warming, and emissions are not caused only by combustion, but also during resource extraction like mining, during transport and during processing. You can see in the table the equivalent CO2 emissions of diverse fuels in diverse countries. The equivalent CO2 emissions of natural gas in the Netherlands are 0.20 instead of 0.18 in the precedent slide. Look also at the differences between the Netherlands and UK when it comes to the appreciation of biogas, or the difference for wood in the 4 countries. Both are combustible renewables for which the discussion is ongoing on how far they can be considered renewable, as their rate of depletion is higher than the rate of replenishment. Each country has also different policies when it comes to sustainable forest management. These values are updated regularly at country and world level. This brings us to the end of this lecture on primary energy and CO2 emissions. In the 2 other parts of the essentials, you will learn more about the working principles and CO2 emissions of the different systems. Thank you for your attention.